Today I continue with chapter 7 on Fourier pairs. But before I start new talks, I'd like to quickly review what we had. Then yesterday we started with, I guess, I think you had an announcement to make about the exam, right?
Yeah, exam is tomorrow from. For all other details, check website.
Check website.
No calculator, no formula sheet.
I think you'll be allowed that table. Yeah.
We're given a table.
We're given a table at the end of the exam, right?
Yeah.
What I saw in the past exam.
Yeah.
No.
Let's continue. We learned yesterday that Fourier transform, the Fourier concept can be applied to not only periodic signals but aperiodic signals. So if ft is periodic, then we know that we can actually decompose or write ft in a CD and Fn was called Fourier series, right? Fourier coefficient. So we could calculate it easily using this integration over only one period. Right. So this is what we do for periodic signals. And then we learned that if you have a periodic signal, if you look at the coefficients, you will have discrete coefficient if you plot it over omega, which omega is n omega 0, then what you will have is this. At n equal 1, you have usually the maximum, this is the fundamental, and then it drops. Okay. And 2, 3, 4, 0, minus 1. Then yesterday I introduced another kind of or sort of signal which was no longer periodic and it was called aperiodic. So for aperiodic signals we learned that we can still extend Fourier transform, Fourier series to what we call it Fourier transform. And it's a little bit different, but I mean this 1t is no longer here. But instead we have 1 over 2 pi here. Integral is no longer over one period, but as this summation goes from minus infinity to infinity, this integral goes from minus infinity to plus infinity, and we have f omega, which is a converse version of this discrete series, j omega t d omega. So we integrate over frequency. And then f omega, which is known as Fourier transform, is calculated instead of being on one period, was going from minus infinity to plus infinity, and ft d minus j omega t dt. So you can see the difference. No longer is summation, instead we have integrations. And you learned this in high school, or I don't know, in calculus 1, 2, maybe when you were a freshman, that any integral can be calculated by computer using a summation, Riemann summation, Riemann series. So these two are analogous. They are kind of equivalent because I mean we can do this using summation in computer. Computer cannot do integration. Instead, it breaks it into series and calculate. So these two are almost similar. Then what we learned here was, if you look at this, if you have a periodic signal, we should expect. If this was a quiz, you should expect that this cannot be assigned to an aperiodic signal. This goes to a periodic signal, right? If it was aperiodic, then this should have been like this, continuous, right? So periodic, discrete, aperiodic, continuous. And this is omega. It's easier from now on. You don't need to work with discrete numbers. For brain, it's much easier to work with continuous numbers. Now, I mean, if you like to learn it, if you like to visualize it, this is very difficult, discrete. So usually in your brain, you break it to, I mean, you try to think of it as a continuous. So that's what you usually do to see the pattern, right? That's what your brain does, it's interpolation. So this is easy, it should be easier for you. Then another thing that is important was if you have a system and F goes to your system, let me just write down this. This was known as Fourier Transform. This one. And this one was inverse Fourier Transform, Fourier Transform. And these two together make a pair. And we learned that we can show that by a bidirectional arrow like this. So Ft, F omega, Ft, right? You can go to the other way, come back, right? And then we learned that we have Ft, and we use that Ft as an input for a LTI system. What we get as output is Yt. If the response of this system is H omega, if this F can be written as F omega, then here we have Y omega, which is F omega H omega. You guys know about convolution, right? Convolution?
No.
Oh, you don't know about convolution. Okay. So never mind. I mean, I'm going to teach it today, but it's in the table. I thought you know it. So what convolution is, if you have a signal like Ft and you pass it through any system which is linear time invariant, that system in time domain has a response. They call it impulse response. If Ft gets convolved with Ht, what you get is Yt. So in real life, this is what really happens. Your signal gets convolved with the impulse response of your system, and then you get output. I mean, you have the output, Yt. So I'm going to teach you today that this convolution, they call it convolution. And the way they show it is this. Ft convolved, let's say Ht. It's an integral. Is f tau Ht minus tau d tau, and tau goes from minus infinity to plus infinity. That's the definition of convolution. It's just one integral. That's what convolution stands for, like this integral.
I have a question.
Yeah.
So can Fourier transform and Fourier series be applied to complex input signals?
Complex
Complex
input signals, yes. Complex shape signals, right? You mean the shape of the signal is complex or the value is complex?
The value is complex.
Oh, yeah.
So how can plot the complex input signals?
Oh, how to plot this? That's a very good question. If you have a complex number, you want to plot it, you should plot absolute value and phase separately. Phase and magnitude. Okay.
So the complex input signals will still be complex signals after the Fourier series.
Possibly. Yeah.
But with the H of t, can't you just plug H omega into the function and just get out?
Sorry, can you repeat your question?
So H of omega inside the LTI.
H omega.
Could you just transform it into H of t using that equation?
Yes. And then use this convolution to do it, right? Is that what you mean? Or? This Ht is the Fourier pair of this H omega. Yes.
Yeah.
It's our pair. So you can do it in Fourier domain, you can do it in time domain, depends on you. So you have two choices. You can pick. And sometimes this is very difficult to perform because you need this integration, and this integration is difficult to do. But in frequency domain, it's very easy. Your eye every day is doing this for you. Oh, never mind. It does some FFT, Fourier Transform, and then creates an image when you can see things. This convolution is happening, but never mind. So if there is any question here, but just forget about this for now, I guess. I thought you learned this, but if not, you don't have to. Just, I mean, it's just for your information.
No, I think the answer to your question is that it's a property. Given an f of t, if I want to calculate y of t, I can transform f of t to f of omega. Given h of omega, I can find y of omega using that formula right there, and I can apply an inverse Fourier transform to get y of t.
That's right.
Or I can do it directly by using the convolution formula.
Yeah, today you will learn that this is equivalent to f omega h omega. Mean convolution can be written as this multiplication in frequency domain. So time domain convolution is equivalent to easy multiplication in frequency domain. Okay, there was another question. Okay, yeah.
So is it ever going to be easier for us to do the convolution directly, or are we always going to do the Fourier transform and do it that way?
That's a good question. Most of the time it's very easy to do in the time frequency domain, but there are certain signals. I always prefer to do this one because computer makes this very easy for us to do, because I mean you won't learn this in this course, but instead of doing Fourier transform, we do fast Fourier transform, FFT. I don't know if you heard this name or not, but FFT is very easily implementable. You can implement it on computer, MATLAB, C++, any coding language. You can easily implement FFT, and then if you have your signal, that FFT applies to the signal, you have f omega, and the other one h omega, and then you can calculate y, and then do one IFFT to convert this back to y. So computer likes the top one better than the time domain one. Convolution usually is time consuming, difficult to do if you want to do it. Because I mean, I don't want to go through it because it's a window and you should move it and then multiply and then sum. It's tough. It's tough to do. Okay, let's move on to one more thing maybe I should mention here is, I don't know if I did yesterday or not, but there is a condition because it is sufficient for ft to have Fourier transform if ft is absolutely integrable. Yeah. If we go from minus infinity to plus infinity, if this number is smaller than infinity, then ft, we can conclude f omega exists. Okay? But this is not a two-way arrow, it's only one way. So if f omega exists, it does not mean that this inequality will be satisfied. This is not true. Because, sufficient, if you're a mathematician, enough of sufficient is two ways. But it's just, if I say sufficient, it doesn't mean the other way can be applied. So be careful about the words you hear. If it has enough and sufficient, it means that you could go backward. But here, if you find a signal which can, if you integrate from minus infinity to plus infinity, and the value is less than infinity, you can close your eyes and say f omega exists. But if I give you an f omega and I ask you, can I conclude that there is the ft equivalent to f omega is integrable, absolutely integrable, you cannot answer it. It's not yes, you should test it. And I can give you an example. The example is ut, unit step function, right? It was another part of the course I taught yesterday. I introduced a few functions, ut, you remember it, right? Rect function, delta function, and sine function. So ut, if you integrate it from minus infinity to plus infinity, dt, it's gonna blow up, right? Because it's gonna go to infinity. You're summing up 1, 1, 1, 1, 1, and eventually it's gonna be infinity, right? But ut has a Fourier transform. There is a transform for ut. this rule is one way. So if we could find f omega, doesn't mean that ut is absolutely integral. Don't worry, I will teach ut today. I mean, if you don't know what is the Fourier transform for ut, no worries, you will learn today.
Doesn't that imply that it's backwards?
Sorry?
Doesn't that imply that it's backwards? So if it goes to infinity, the unit step function, then that means that the arrow can only go the other way around.
It means that this we cannot conclude that f omega exists or doesn't exist. This condition is not satisfied by ut, right? But it doesn't mean that there is no Fourier transform. So if the condition is not satisfied, it doesn't mean that the Fourier transform does not exist. If it's satisfied, it means that it exists, absolutely exists, right? You saw the difference? If this is satisfied, this exists. But if this is not satisfied, you cannot conclude that it doesn't exist. No, you cannot conclude it. So let's go to, continue with the Fourier pairs. And I'm gonna just introduce a few important properties of Fourier transform. It's table 7.1 in your book. And you can look at it later if, I think in exams in the future, it will be provided. But I'm gonna just go over them. Some of them are very easy, and you just know them, right? Just amplitude scaling. This is a property which says that if you have ft, which gives you f omega, then if I scale this ft by c, while c is a constant number, doesn't matter if it is real or imaginary, as long as it is constant, Fourier transform is going to be scaled. That's very simple, right? Second one is addition. If I have ft and gt, while ft has a Fourier transform f omega and gt has a Fourier transform g omega, if I sum them up, ft plus gt is gonna give us f omega plus g omega. Third one is Hermitian. It's called Hermitian. And it says that if your ft is real, then your f minus omega should be f conjugate omega. This is pretty much what the definition of Hermitian is, almost. I mean, it is the definition of Hermitian. So if your ft is real, your f omega should be Hermitian. If you conjugate it and switch the omega to omega minus, this should be. They are very simple to. It's very simple to prove it, and I'm not gonna prove it because it takes forever if I want to go over all of those steps. But it's very simple. Just if you look at the definition, I already erased it. You can see those things are correct, and they were tested before. And you may ask yourself why I am providing these properties and why we need to learn them. You know, it's you can just not use any of these properties and always go back to those definitions I provided and calculate any function I give you. You can do the calculation from step 1, integration, right? But it may save you so much of time if you can apply these properties. And if you, for instance, if you learn what is the Fourier transform for ft, let's call it u omega for now. Usually it is s. Okay. Then if I learn what is the Fourier transform for e minus t ut, let's call this s1 omega. So if in your test you are asked to calculate the Fourier transform of this function, you don't need to repeat these steps. You can just easily say S1 plus S2. Right? That's why we're learning these properties for future. When we know enough important transformations, I'm going to tell you some of them based on as much as I can, like UT and delta and others. If you know them, you just need these properties to calculate. Then you can calculate many other functions. So the other one is even and odd. Even and real, maybe. If ft is even and real, then we can conclude that if omega should be even and real. And the fifth one is odd and real. We can repeat the same thing, just say instead of even, say if it is odd and real, then if omega should be odd and real. Sixth property is symmetry. This is very important and a little bit confusing. So if you have ft, which provides you with f omega, make sure you understand this one. It's a bit difficult. Ft is gonna be, so this ft is going to be 2 pi, I think, f minus omega. I should do. But this property is an important one. Yeah, it's nice. So, but make sure that you know what's happening here. Right? This f, I take this f and replace omega with t, then I can go and I say this f in time domain has a property, has a transform, which is my f in time domain in omega domain. Did you catch the point? What's happening here in this one? Yeah.
So if you just switch the variables of those functions that you
Exactly.
that
I
x
switched the
right hand side
variables.
is true.
Very good, explanation. I switch the variables, and I can decide. I can say after switching that f, the capital F, which is the 2 Fourier, if it was in time domain, it had a Fourier transform in omega domain, which was similar to the other one in time domain. So I'm going like let's give you an example. If this ut has a property, let's add this for now. It's ut minus at has a transform like this, right? So if I ask you an exam, what is the transform of st now? Okay. Can you answer this?
2 pi
Okay, 2 pi u omega, right? U minus omega. E plus a. I just took that 2 pi. So what I did, I put this here. It's nice property, very useful, but somehow confusing. And the time scaling. Time scaling is another one. Again, if we have ft with its pair f omega, now what happens if I scale ft with c? C is a constant real number. What happens if I do this scaling? I'm gonna get this. another one. And time shifting, I think this is also very useful. If I won't repeat this. If ft is this, and then if you f t minus t0 or t naught, you will get f omega. Can you guess? You had this in Fourier series. Sorry, yeah, Fourier series. If you shift in time, what do you get in here? Not time t naught. Oh, yeah. Go ahead. E I have j omega t naught. Yeah. It's very useful. So what it's trying to tell you, it says that if you do time delay, this is time delay, right? If you delay your signal in time, in frequency domain, you're shifting the phase of the signal. This is the phase. This guy, this exponential term, it does not add or remove from your magnitude. The only thing it does, it changes your phase. Whatever the signal, the phase of the signal was, now is shifted backward. Minus is backward. So delay in time translates to phase in frequency domain. Okay? So your signal is going through your system, and your system is slowing down or shifting back your signal. It's equivalent to shifting your signal in frequency domain. So I can use this to design something, call it phase shifter. Okay. So if I have a signal like ft, and it has a phase, let's draw ft like digital, right? It's like this. Okay. In here at t equal to t0, it drops, right? That's the edge. It's very important for us to detect this in digital design. Then if it goes through phase shifter or delay, time delay, what's gonna come out is that t0 is gonna move back. Let's call this t0 and the delay td for now. Then this guy is gonna be delayed by t0 minus td. So it moves backward comparing with this. It moves this way. And this guy also moves the other way. By td. So we're moving back everything by td because this phase shifter is introducing some delay to the signal. So the observer, whoever, the IC, processor, whoever is here, feels some delay comparing with what's happening in here. So if you're changing the edge in here, at time equal 1 second, this guy will feel it 1 plus td seconds later. So it can get ready, can do other things until this reaches it. So we need this time delay and phase shift in our system. So that's what happened. Phase shifter, they call it phase shifter, but really it's a time delay, right? They designed the phase shifter to shift the phase, which is the equivalent to time. They're shifting the time. It's offline now, no longer online, real time. Any question? Can we design a system that gives us positive input? So before I send my data here, this guy can predict me. Can we? No? Okay. Really? Well, what's wrong with that system?
Predicts the future.
Yes, forecast the future, right?
Artificial intelligence.
It looks like I have a rock in my hand and I throw it toward that window, and the window breaks before the rock reaches it. Window predicts what's going to happen, right? That's what that T plus means, right? Predicting the future. Before it happens, it happens. Before it reaches there, it happens. But this is happening in many systems you have today. They predict the future, and if not, you probably could not use many of your devices And because they use adaptive filters. Adaptive filters, they have such a thing, they try to predict and adapt. So that happens because whatever your data, because you have a memory, you save this data in your memory. If this guy has access to whatever it was in past, like let's say I start saving or recording some data. When I call it recording, it means that whatever happened in real life, with some on some delay, I save it in here, right? So all data in my memory is accessible for my system, right? My system can't go in time up and down. Comparing with this, not with this. This guy is out anymore, right? We don't have access to real life, right? So in here, we again define time as equals 0 in here. This is the first line that is saved in the memory. And then in here is the last line at time equal 10 seconds, for instance, right? So to you, when I say time equals 0, you think everything is happening at time equals 0, but this is not what exactly it is. We save the data from 0 to 10, so your system can somehow go backward. Not backward, no, can go forward. And when it's working with time equals 0, it can use data from time equal 5. That's what makes those adaptive filters possible. So this is kind of buffering. You buffer the data, the time reference is from 0 to, for instance, another number. This is your buffer length. So then you can move, and you can go forward or backward in time to analyze this data, to apply some filtering to this in the best way that you can. So it's possible. However, it's not casual, right? Or casual. And that's a word, I guess you probably learned it before. It's like, I don't know if you learned it or not. You know about causal systems? Casual? How do you pronounce it?
Causal.
Causal? Okay.
And it's CAUSA.
Cat here?
CAU.
C. Okay, thank you. Very bad. Very bad English. But thank you for correcting. Whatever this system is what we already learned. In future, if you come up with this causal system, it means that the window cannot be predicting the future in real time. But in offline, you can do it. This is kind of offline, right? If I remove this buffering, your system is connected to real life, it cannot go forward. But if I have a buffer, it can go forward and backward because you define your reference.
So is that like text prediction?
What's that?
Like text prediction? Or like
Can be.
research?
Can be. I'm not sure if that is one case or not, but you can search on that. See. I think this mostly is for adaptive systems, which they work in a very noisy situation, and they have to recover the signal. So they have to have some idea about the statistic of the signal, and if they don't have enough information of the signal, they cannot predict it. Yeah, I guess I went so far away from what I was teaching. Okay, 9 is frequency shift. So frequency shift should not be difficult if you know time domain. If you shift in frequency by omega 0, what you're gonna get is in time domain omega naught t. And there are more. I don't know if you want me to write all of them, but I ask you to just go over the table. That's the best, I guess, and it's much better than my handwriting. And it's organized. There's one thing I probably should write, and it's a convolution. It's number 13, which talks about convolution. I leave this empty for you, and time convolution, which you know it now, right? Which if ft is convolved with gt, and ft has f omega, and gt has g omega, what we get in frequency domain, it looks like you multiply it. It's the big convolution. Okay. I have maybe 20 minutes to. You can use some of these properties and calculate Fourier transform of some popular signals, useful signals.
What's the definition of convolution?
Yeah. What was it? I already wrote it, right? You want me to repeat it or?
No,
What is it? What is convolution?
Convolution. Listen, the definition is like you have two signals. I don't know about like if you're looking about etymology. I mean the terminology. What was the meaning of the convolution? It means, to me, it means move it and multiply it. Move the signal, multiply it with the other signal, sum them, and then again do it and do it and do it. So what happens in, if I want to show you this way, if you have ft, let's say ft is this signal, okay? It's very narrow in time, right? And then you have another signal, what? Time, and this is gt. What really convolution means, if the gt is this guy, so what really ft mean, convolution means that you start moving this guy from here. You take this guy here, okay, and start moving it. All right. So, and then multiply this with the value of gt, which is 0 in here, right? 0. So you get 0, 0, 0, 0 until this guy reaches here.